Hello, my name is Caio Morais, and I'm a researcher and physiotherapist at the Federal University of Pernambuco. Today I'm going to talk about how to set PEEP using pressure volume curves and electrical impedance tomography. The pressure volume curve is a method introduced over 50 years ago to measure the global elastic properties of the lung. To minimize the resistive factors of the tracheal tube and airways, a very low constant flow rate is applied. Typically, the PV curve has a sigmoidal shape with three sections divided by two key points, the lower inflection point and the upper inflection point. In the past, we assumed that the lower inflection point represented the region where previously collapsed lung tissue is recruited. The linear section of the inflection curve indicated the progressive inflection of the already recruited alveoli. And any point above the upper inflection point signified lung hyperinflation. Thus, it was suggested to set PEEP a few centimeters of water above the lower inflection point to prevent lung collapse. Our current understanding of the physiological phenomena captured by the PV curve has changed significantly. For example, we know that lung recruitment can occur continuously throughout the inflation phase of a PV curve rather than only at the point indicated by the lower inflection point. Electrical impedance tomography is a non-invasive, radiation-free medical technology that provides information about regional distribution of ventilation through electrodes placed on the patient thorax. With EIT, we can precisely identify change in lung morphine function and measure a variety of physiological variables in different lung regions. For example, it enables the detection of pendiluft, an important type of intrapulmonary asynchrony, as well the monitoring of lung overdistension and recruitable collapse at different levels of PEEP. The main difference between these two methods is that EIT provides regional information about lung function, while the PV curves describes a global behavior of the lung. This is indeed the primary limitation of the PV curve. For example, lung recruitment and hyperinflation can occur simultaneously at different lung regions. This opposing phenomenon can affect the slope of the inflection curve. Consequently, you may not detect hyperinflation in a patient by looking at the PV curve alone, as the upper inflection point may not be visible if the lung recruitment also occurring at the high airway pressure. It would be much more informative if we could visualize the PV curve for different lung regions using EIT. This would allow us to precisely identify regions that are opening and hyperinflating at the same absolute airway pressure. Although the PV curve is a global measurement, using a low flow during the inspiratory and the expiratory phases, known as the low inflation-deflation maneuver, we can reveal the pulmonary hysteresis. The distance between the inflation and the deflation limbs reflects the lung viscoelastic behavior due to the stress relaxation and change in the air-liquid interface. In theory, an increase in lung hysteresis suggests lung recruitment along the inflation limb, providing some indications of lung recruitability. However, the PV curve inflection-deflection maneuver alone cannot define the level of PEEP needed to simultaneously avoid both collapse and overdistension. EIT enables the estimation of recruitable alveolar collapse and lung overdistension during a decremental PEEP maneuver. At each PEEP step, the algorithm calculates the pixel compliance. Then, it determines the percentage of change in compliance for each pixel relative to the best compliance. Then, collapse is identified when a reduction in PEEP causes a decrease in a pixel compliance after reaching the point of maximal compliance. Conversely, a pixel is considered to be experiencing overdistension if its compliance is increased as PEEP is reduced until reaching the point of maximum compliance. This measurement is important to avoid two well-known mechanisms of lung injury, atelectasia and lung overdistension. Since both phenomena are potentially harmful, PEEP is usually set to minimize both overdistension and collapse, aiming for a crossing point between them during a decremental PEEP trial. Recent experimental and clinical studies suggest that this method may provide better respiratory compliance and reduce mortality compared to standard methods for PEEP titration in patients with ARDS.